In this video, we will practice using the P-series test and the integral test to determine whether a series converges or diverges. This is a BC-only topic. If you have not yet watched the introductory lesson, you should definitely watch that first. This video will make a lot more sense if you do. You can either click the link that appears in the upper right-hand corner or find the link in the description. Confirm that the integral test can be applied to the series. Then use the integral test to determine the convergence or divergence of the series. The first step is to write function f of x by replacing the n with an x. Note that the integral test can only be applied if f of x is positive, decreasing, and continuous eventually. 3 to the negative x power can be written as 1 over 3 to the x power, an exponential function whose graph we know looks like this. So it is positive, decreasing, and continuous. Stating that f of x is positive, decreasing, and continuous is the first step you have to do before you can use the integral test. The integral test requires us to determine whether the improper integral from 1 to infinity of f of x dx converges or diverges. If this improper integral converges, then the series also converges. If the improper integral diverges, then the series also diverges. We are using the integral from 1 to infinity because the series goes from n equals 1 to infinity. The first step of analyzing an improper integral is to find the antiderivative, which I will call capital F of x. We are about to use the following memorized rule to find the antiderivative of 1/3 to the x power. The antiderivative of a to the x dx equals 1 over the natural log of a times a to the x plus c. In this case, a is 1/3. So the antiderivative is 1 over the natural log of 1/3 times 1/3 to the x power plus c. Next, we need to find the limit of the antiderivative as x approaches infinity and the limit of the antiderivative as x approaches 1. The expression in the front is not changing because it's a constant. What about 1/3 to the x power? As x approaches infinity, 1/3 to the x power gets smaller and smaller and smaller because 1/3 times 1/3 times 1/3 is getting smaller and smaller and smaller. So the overall value of the expression approaches 0. So that's the limit. By the way, notice that we can ignore the plus c as we evaluate these limits. For the second limit, we can do direct substitution. Plugging in 1 for x gives us 1 over natural log of 1/3 times 1/3. So that's the limit. When the upper limit and the lower limit both equal a number, the improper integral converges. So if this was just an improper integral problem, I would say the integral from 1 to infinity of f of x dx converges to the big number minus the small number. To justify whether the series converges or diverges, we say since the integral from 1 to infinity of f of x dx converges to 1/3 over natural log 1/3 minus 0, the series also converges by the integral test. Of course, you don't have to put the minus 0. I'm just emphasizing that the improper integral converges to the bigger number minus the smaller number. Number 8. Before we get started on the integral test, we need to rewrite this series using sigma notation. So we are going to need to find an expression for the nth term. We see that the numerator is always 1, so far we have this. I notice that the denominators are increasing by 2 each time. This is called an arithmetic series. The expression for the nth term will be linear. I'm looking for an expression an that represents the nth denominator. I know it's going to be linear, so I'm thinking y equals mx plus b. In my expression for an, the m is going to be the common difference of 2. So I know an is going to equal 2n plus something. This b value can be found by subtracting the 3 minus the 2. So this is going to be 2n plus 1. So this series can be written as the sum from n equals 1 to infinity of 1 over 2n plus 1. In order to use the integral test, we must first write a function f of x by replacing n in the rule with x. Then we must state that f of x is positive, decreasing, and continuous eventually. F of x has a vertical asymptote when x is equal to negative 1/2. But for values of x greater than negative 1/2, f of x is positive, decreasing, and continuous. Next, we need to find the antiderivative, which I will call capital F of x. We can do this using mental U-Substitution. If u is 2x plus 1, then we have 1 over u. The antiderivative of 1 over u is the natural log of the absolute value of u. However, we always have to divide by u prime. And in this case, u prime would be 2. So we can divide by 2 by putting a 1/2 out in the front. And don't forget the plus c. Next, we evaluate the improper integral from 1 to infinity of f of x dx. We do this by finding the limit of the antiderivative as x approaches infinity, the upper limit, and the limit of the antiderivative as x approaches 1, the lower limit. You can ignore the plus c for this. As x approaches infinity, this expression just gets bigger and bigger and bigger. That means the limit of the antiderivative as x approaches infinity does not exist. If even one of the limits does not exist, it means the improper integral diverges. So there's no need to find the other limit. In summary, we say since the improper integral diverges, the series also diverges by the integral test. For number 12, our first job is to rewrite the series in sigma notation. So we are going to need to find an expression for each term an. In the numerator, the first term is 1, the second term is 2, the third term is 3, and so on. That means the expression for the numerator is simply n. The expression for the denominator is going to be more tricky. There is no common ratio that takes me from 4 to 7 and from 7 to 12. So how about the common difference? Well, from 4 to 7, that's plus 3. And then from 7 to 12, that's plus 5. So there is no common difference. However, I feel like I am seeing a pattern. 3, 5. I'm betting that the next jump would be 7. In other words, I bet the next term would be 4 over 19. So there is no common difference if we are looking at the first differences. However, if I look at the difference between these differences, I'm talking about the second difference, and this is plus 2. When the second difference is a common difference, then that means the expression we are looking for is quadratic. So it's going to have something to do with x squared. Or rather, instead of saying x squared, it has something to do with n squared. So let's look at n squared in each case. 1 squared is 1, plus 3 would give me 4. 2 squared is 4, plus 3 would give me 7. 3 squared is 9, plus 3 would give me 12. Just for fun, let's check the extra term. 4 squared is 16, plus 3 will give us 19. So the series can be written as the sum from n equals 1 to infinity of n over n squared plus 3. Let's define f of x as x over x squared plus 3. F of x is always continuous because x squared plus 3 is never 0. There's no vertical asymptote. And for values of x greater than 0, f of x is positive, and decreasing. So we can say that f of x is positive, decreasing, and continuous eventually. We are building up to evaluating the improper integral from 1 to infinity of f of x dx. But first we need to find the antiderivative, capital F of x, of f of x. You can probably find this antiderivative in your head using a mental U-substitution, but I'm going to show it and then just erase my work. Imagine that u is x squared plus 3. That means u prime is 2x. So the original expression x over x squared plus 3 now becomes x over u. Instead of writing dx, we write du over u prime. In other words, du over 2x. But then we notice that the x's cancel each other out. This 2 in the denominator is going to come out to the front as a 1/2. So we have 1/2 of the integral of 1 over u du. This is 1/2 times the natural log of the absolute value of u. Remember, u is x squared plus 3. So this is the antiderivative. We can evaluate this improper integral by finding the limit of the antiderivative as x approaches infinity and the limit of the antiderivative as x approaches 1. However, as x approaches infinity, this expression just gets bigger and bigger and bigger. So the first limit does not exist. If even one limit does not exist, it means the improper integral diverges. So we don't need to find the second limit. In summary, we say, since the improper integral diverges, the series also diverges by the integral test. Number 16. First, we define f of x like this, and we state that it is positive, decreasing, and continuous. Because natural log is only defined for values of x greater than 0, we know f of x is positive and continuous. And because the denominator is getting bigger and bigger while the numerator is a constant, we know that f of x is also decreasing. Ultimately, we need to evaluate the improper integral from 2 to infinity of f of x dx. But first, we need to find the antiderivative of f of x. Let's use U-substitution. Let's let u equal natural log x. In that case, u prime will equal 1 over x. If we do this substitution, we have 1 over x times the square root of u. Instead of dx, we will write du over u prime. So that's du over 1 over x. Notice that x times 1 over x cancels itself out. So now we have the antiderivative of 1 over the square root of u du. Let's rewrite this as u to the negative 1/2 power. Using the power rule of integration, we add 1 to this exponent, which gives us 1/2. Then we divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2. Replacing u with natural log x gives us the antiderivative equals 2 times the square root of natural log x plus c. To evaluate this improper integral, we need to find the limit of the antiderivative as x approaches infinity and the limit of the antiderivative as x approaches 2. However, as x approaches infinity, this expression just gets bigger and bigger and bigger, so the limit does not exist. If even one of the limits does not exist, the improper integral diverges, so we don't need to find the second limit. In summary, we say, since the improper integral diverges, the series also diverges by the integral test. Number 20. First, we define f of x like this, and we state that it is positive, decreasing, and continuous eventually. F of x has a vertical asymptote at x equals -2, but for values of x greater than -2, it is positive, decreasing, and continuous. Eventually, we need to evaluate the improper integral from 1 to infinity of f of x dx. But first, we need to find the antiderivative of f of x. Let's do U-Substitution. If u is equal to x plus 2, then u prime is just equal to 1. So, doing that substitution, we have 1 over the square root of u du. Normally, I would say du over u prime, but that's just 1. So we have this. Let's rewrite this as u to the negative 1/2 power. Using the power rule of integration, we add 1 to the exponent, which gives us 1/2. Then we divide by the new exponent, and dividing by 1/2 is the same as multiplying by 2. And don't forget the plus c. So the antiderivative is 2 times the square root of x plus 2 plus c. To evaluate this improper integral, we first must find the limit of the antiderivative as x approaches infinity, and then the limit of the antiderivative as x approaches 1. However, as x approaches infinity, this expression just gets bigger and bigger and bigger, so the limit does not exist. If even one limit does not exist, it means the improper integral diverges, so there's no need to find the second limit. In summary, we say, since the improper integral diverges, the series also diverges by the integral test. For number 28, we need to explain why the integral test does not apply to this series. This problem is calculator active. We define f of x like this. Remember, the integral test only applies if f of x is positive, decreasing, and continuous eventually. Let's take a look at f of x on the TI-84. I'm betting if we analyze the graph, we'll find that it breaks one of these 3 conditions. Let's hit the y equals button and type in f of x as y1. Let's see, alpha y equals enter creates a nice fraction, and we will do sine x over x, and the whole thing is going to be squared. Let's take a look at the graph by hitting zoom 6. This graph is too small to see what's going on, so let's adjust the window. First of all, we only need to know what's happening eventually, so let's only look at x values that are greater than 0. Also, the y values seem to max out at 1, so let's only look at y values that are less than 1. Hit the window button. Let's let x min be 0. X max can be 10 still. Let's let the minimum y value be 0. It didn't seem to really go below the x-axis, so let's let y min be 0. Let's start with a y max of 1 and see what we get. I think I can already see what the problem is, but I think we can see even better if we stretch out the x values. Let's look at more x values, and let's zoom in even tighter on these y values. So right now we're at a maximum y value of 1. Let's make it like 0.1. So hit that window button. Let's let x max be 20. Alright, let's double the x values. And let's let y max be 1/10 of what it is now. So let's let it be 0.1. And let's take a look. Notice how the graph of f of x seems to bounce like a dropped ball. It has intervals of increasing and then decreasing, and then increasing and decreasing. F of x will continue to alternate between increasing and decreasing intervals forever. In summary, we say f of x oscillates between increasing and decreasing as x approaches infinity. Since f of x is not decreasing even eventually, the integral test does not apply. The next few problems are about p-series, which can be written in the form a over n to the p power. So, for example, the sum from n to infinity of 2 over n to the third power is a p-series. If you have a p-series, you can use the p-series test, which says, consider the value of p. If p is greater than 1, then the series converges. If p is less than or equal to 1, the series diverges. This kind of makes sense because p is in the denominator. So if p is greater than 1, that means the denominator is getting bigger and bigger. So the overall value of the expression is getting smaller and smaller. And we are not surprised that the series converges. On the other hand, if p is less than 1, that means the denominator is getting smaller and smaller. So the overall value of the fraction is getting bigger and bigger. So we're not shocked that the series diverges. Determine the convergence or divergence of the p-series. So for number 34, we notice this is a p-series with a p-value of 5 over 3. So we start by writing p equals 5 over 3. But what is the significance of this? We must mention that p is greater than 1. And since p is greater than 1, the series converges by the p-series test, which we can abbreviate PST. For number 36, let's start by rewriting this series in sigma notation. So we are going to go from n equals 1 to infinity, and these are all fractions with a 1 in the numerator. In the denominator, notice that we have the cube root of 2 squared, 3 squared, 4 squared, etc. Also, remember that a fractional exponent is in the form power over root. So if I have an expression like this, p is the power, so that's going to go in the numerator. R is the root, which will go in the denominator. So these roots can be written as 2 to the 2/3 power, 3 to the 2/3 power, 4 to the 2/3 power, etc. That means this series can be written as the sum of 1 over n to the 2/3 power. This is clearly a p-series with p equal to 2/3. This is not enough. We must mention the significance, which is that 2/3 is less than 1. And since p is less than 1, the series diverges by the p-series test. Number 38 is a p-series where p is equal to pi. We must mention the significance, which is that p is greater than 1. Pi is approximately 3.14, which is obviously bigger than 1. So the series converges by the p-series test.